Do you see the picture, Adam? So birds called, and in France we say the pinson de Darwin, Darwin's birds. And so they are the difference between these birds are based essentially on the big size here. But and the idea of Darwin is that if even if they are very different, they all come from from a unique ancestor. But of course, between this ancestor and all these different offspring, there is a very, very long time, including a lot of environmental changes and a lot of ecological interactions, and which lead to evolution. And so our question was, if we observe at some time t this such sort of diversity, are we able to guess what was the characteristic of the ancestor? So that was the question we had in mind. And so on the right, I show you what essentially what is a parallel, the actual parallel with such picture, that is a phylogeny. I don't remember the perhaps of birds, but it's a phylogeny which indicate from here you have molecular information on actual species, and if you come back on each line here, you can find, of course, it's small, the history, the ancestral history of each until the main ancestor which are represented here. Okay, and so that was our aim. So I just like these lines because they are due to Darwin, and essentially our probabilistic model was based on these sentences, which are in the, I think, in the introduction of his famous book on evolution theory. And that's what he said. As many more individuals of each species are born than can possibly survive, and as consequently there is frequently a recurring struggle for existence. So here you have the competition between individuals, either for resources or to share, for example, females or so on. And so that the ecology of the problem, we could say, it follows that any being, if it varies however slightly in any manner profitable to itself. So here we introduce the notion of variation, small variations, which are due essentially to mutation, which arrive at the molecular level. And so here you can imagine that you have mutants which arrive in the population under the complex and sometimes varying conditions of life. Here appear the environmental conditions. So we will have a better chance of surviving and thus be naturally selected. From the strong principle of inheritance, any selected variety will tend to propagate its new and modified form. And I think that all is summarized, all the main principles for evolutions are summarized here. Since you have heredity, so the mechanisms are heredity, which is explained here. You have variations due to mutations, and you have competition between individuals. And there is, from all these mechanisms, which leading to different trade-offs, in fact, we can, all these mechanisms will yield the evolution process in a long time scale. Okay. And also in this description, so you have different phenomena which essentially are random at different scales, which can play a main role, in fact, in the modeling, because you have mutations at the molecular level, you have individual demography, birth, death, mating for sexual species, exchange of information, for example, for bacteria, migration, and so on. So, and you have environmental variations. And so you have essentially three main scales, time scales and size scales here. and in each level can be random. So here we will include in our model, of course, birth and death of individuals, since we consider population dynamics, mutations, and we will also include some environmental change. But for this talk, I will take a very strong assumption on this environmental change, which will not, as in this picture, stochastic, but it will be deterministic, main on a lot of literature and PDE. But of course, as I said, it's a work in progress, and we have a lot of improvement to we have a lot of open questions related to my simple model. Okay, but keep in mind that we have all this structure in the model. So in quantitative genetics model, usually, and we will do that, individuals are characterized by quantitative parameters called traits, which describe or summarize the genetic of phenotypic information. And so that is here written, it's this X. And we have some transitory equilibria in evolution if there is a sort of trade-off between the variability and the density of individual in the population and the mortality rate. And here, for example, you can see that there is here an optimal trait from the point of view, from the evolution point of view, since here this trait you see is the optimal for the density of trait in the population, but also because it decreases, at this level, the mortality rate is smallest as possible. And so there is a balance between the mutation, which creates variability, and the selection, which usually impose some mortality conditions. Okay. So and so it's good, I think, to keep such sort of picture in mind. So now so as I said, our aim was to include in our model some environmental change, and for example, ecologists have observed that there are rapid phenotypic changes in populations which are subject to environmental changes, and that such fast evolution may result in adaptation of these populations, and that we want to model first with an individual-based, stochastic individual-based model, but as you will see, it will be related to a PDE point of view, partial differential equation point of view. And so first we will model such dynamics. And second, we would like, as I said at the beginning of my talk, the dynamics in the past of what we call the lineage, which is the genetic history of an individual chosen at random at a fixed time, which is our observation time. Okay, so even if I presented picture with birds, I have to say that my model concerns more asexual individuals, and we will consider a framework where we are in large population. So imagine, for example, bacteria. We know that they evolve very fast, and they are in a huge number. And for example, and here I also speak for our Chilean colleagues, and in particular for Pablo Marquet, because I have the exchanges with Alejandro Mas, who is a mathematician in the Universidad de Chile, working with Pablo Marquet, and they are interested in the data of Tara. You know, Tara is this ocean exploration from the evolutionary point of view. And it seems that in ocean, there are bacteria which evolve very fast, based on the temperature change, which is a gradual change, and also based on acidity change. And since Tara will spend 3 months near the coast, near the Chilean coast, we were discussing on this subject. So it's to see so that our model is, I think, more adapted for such sort of populations that, for example, mammals. So we assume that, as I said, that each individual is characterized by a quantitative genetic or phenotypic real parameters that I will call the trait. So I take a real to simplify the presentation, but it could be a vector of RD. And I introduce immediately a parameter K, which scales the population size. And as I said, I am interested in large population framework, and so K will be large for ecologists or will tend to infinity for mathematicians. And so at time t, so I have a population process, and mean we have birth and death in this population, but at time t, we have n of t individuals. So my parameter will scale all the quantities, but never mind. But I will assume that since I have a very, very large number of individuals, assume, for example, that the resources are fixed, and then the biomass could be represented by 1/k. So each individual will be weighted by 1/k. And each individual has a trait. And here at time t, I describe the vector of traits of my individuals alive at time t, which belongs then to R to the power is the number of individuals in my population at time t. But of course, since the number of individuals is moving continuously in time, it's better to describe the dynamics in time of this population. Instead of considering this vector, we prefer to consider this point measure, which is essentially the same thing, but which will be easier to describe the dynamics. And so my point measure just count the number of individuals alive at time t, so weighted by 1/k. And here I, for each individual I alive at time t, I associate its trait through a Dirac measure on this trait. So, and now I will describe the dynamics of the process. So I have birth, and I assume that I have so here birth, for example, for bacteria is a cell division, and so as I said, it's a sexual reproduction, and I assume that it's clonal in the sense that the offspring inherits of the trait of the ancestor, okay, of the parent, and we assume that this reproduction happened at trait 1. So we have mutation, and here we will model mutation in a very simple way. We assume that during the individual lifetime, the trait of the individual is submitted to many small and subtle variations, and so we will model it by a Brownian motion with a variance, certain variance sigma square. Okay, and I have also death, and the individual dies either from its own die or due to the competition between the other individuals. And so in the death rate, you have a first term x squared over 2, which is the intrinsic death rate, and which depends, as you see, on the phenotypic, on the trait of on the individual trait. And you have this term, which will give non-linearity in the problem, so it's an interaction term, but which is mean field here, and also for simplicity, here I take the total mass renormalized by k, of course, but of the population as to model the interaction between individuals. Okay, so that's in a certain sense, the ecological part of the model here. And now, here, this model is on a fixed environment, And if you forget the ecological term, the ecological death rate, you see that here the mortality rate is x squared, and then it will be, of course, 0 if x is equal to 0. So from the evolutive point of view, the optimal trait is 0, because you have a fixed birth rate and this death rate, which is 0 at 0. Okay, because the growth rate will be maximal at 0. But now, and that was the point of view, in fact, I think introduced in the 1920s years by Fisher to describe the evolution by an optimal trait. And now we want to introduce the environment. And in fact, the environment will change this optimal trait in the sense that the population will try to follow the environment. And the way we model it is the following. We assume, as I said, it's a gradual changing environment, and then it will evolve linearly in time at the velocity sigma c. So c is a new parameter, and sigma is, for simplicity in computation, is the variance of our mutation diffusion, but our Brownian motion, but of course it's just a question of scaling to introduce it here. Okay, and so we assume that the optimal trait is driven by the environment, in the sense that now, including this the environmental effect, the optimal trait at time t will be sigma ct. That means that in our modeling, we will replace the death rate x squared over 2 by x minus sigma ct squared over 2. Okay. And so you imagine now we have a moving optimal trait, and we want to see in these mechanisms with heredity, birth, mutation, death, how evolution will occur. Okay. So I describe with Hans the stochastic models here. And since we assume that K is large, we have an approximation of this stochastic model by a partial differential equation. And so that's now standard to prove that if we consider a finite time interval 0 capital T, then under some appropriate assumption, if K tends to infinity, K, so that means if we have a very large population, then this stochastic population process we introduced earlier is approximated by the unique weak solution of this integral differential or partial differential equation, where you have here, you can recognize the total, the growth rate in the population, the birth rate minus this death rate with the environmental change here. And here you have the interaction between the individuals with, and here it's a non-linearity in this equation. And here you have the diffusion term due to the mutation events. Okay. And what does it mean that we have this approximation? That means that we don't forget that the process we introduce is a measure valued process. That means that if you consider the integral of a certain test function phi with respect to this stochastic measure mu k, minus the integral of phi with respect to the utx, the solution of this PD dx, then it's in probability when k tends to infinity, and for uniformly in time, these two quantities are very close. And in particular, the total mass of nu k is close to the mass of u when k is large. We will use it. So now I will consider the moving framework. So here I was in the fixed framework, and then the environment was moving, but now I want to work at the environmental moving framework. That means that I make I consider a change through this map, which to x associate x minus sigma ct, and we can prove that when k is large, this new measure is approximated by a new density profile, which is obtained from U, of course. And so this new density profile is f of tx, and it is a solution of this equation. So now we replaced x minus sigma ct by x, and that gives us a new term, which is this drift term. Okay, and that will play a role in the study of the equation. So now, on the moving framework, we consider this new equation. And the first things we ask is do this equation. What is the behavior of this equation in long time? And so we are interested in the stationary point for this equation, the stationary equilibrium. And so it's very easy because we have this drift term and this diffusion term to prove that under this condition, 1 minus sigma over 2 minus c square over 2 positive, then there is a unique positive stationary distribution, capital F, which is then solution of this equation. And in fact, in this specific case, it's very simple. We can compute it with hands easily. And it's a normal law. It's a Gaussian distribution, except which there is, it's weighted, but not by one, but by a parameter lambda, which is exactly this parameter. And which is, in fact, you see here, you have a sort of an eigenvalue problem, and the eigenvalue is here, the total mass of F, which is given by this quantity. And what we can note is that this distribution is centered on minus C. It's optimal if X is equal to minus C. Okay, so we can summarize. Remember that Z tilde K is a stochastic process in the moving framework. So normally we have seen earlier that it would be close to so its total mass should be close to the total mass of F of Tx, this quantity. But if we consider as initial condition for f of tx for this equation, the stationary point function capital F, then f of tx will stay equal to capital F. And then that means that if U0 is capital F, then the total mass of Z tilde K will be very close to the total mass of F, that is lambda, which I've computed. That is this expression. Okay. And now, since we know that this quantity represents the nonlinearity in our problem, we can say if we replace this nonlinearity by this number, which is just a given number, we will replace our initial stochastic process by a much simpler process where the dependence between individuals has been replaced by something fixed. That means that we can make a coupling between our stochastic process and a process without dependence between individuals. So before doing that, I will come back to what we observe. That means that the stationary point reaches its optimum in x equal to minus c. So that means that if we come back to u, we can, since we have this relation between u and f, we can see that if in long time u of xt will be close to capital F, our equilibrium taken on x minus sigma ct. And remember, the optimum of f is at minus c. That means that we have a lag between the environmental speed, which is sigma c, and the lag is given by this quantity minus c. Okay, and so that's observed by ecologists that the population usually adapts to the environmental change, but that with a certain lag, with a certain delay, and in our model, this delay is represented by this minus c. The population is always behind its environment, and it's due to this the time it takes to adapt. Okay, so now I come back to my initial question. So we stay in the same framework, and here there are simulation due to Florian Patou. And so what does it mean? So if we have seen that we have this stationary equilibrium for the stationary function for our PDEs in the moving framework. That means that if we simulate the PDE with initial condition capital F, our equilibrium, then at any time we stay with this profile F, which remember it's a Gaussian distribution. And so here we have the green line represent minus C. And so we have a distribution centered around minus C all the time. And so if we forget the stochasticity hidden behind this model, the PD simulation gives this gray cloud representing a population which seems completely stabilized. And the description of this stabilization is due the density profile capital F. Okay, but now we have seen that this PDE is an approximation of the stochastic model, and if we can also simulate directly, it's easy to do the stochastic process. And since K is large, for example, we can take K around here it's 5,000 individual, I think, at the beginning. We assume that at the initial conditions, the initial of repartition of individual is close to the density profile capital F, and we simulate the individuals. And now we consider this observation time, capital T. And so since we have simulated all the individual trajectories, we are able from the individual living at time t to observe what is the trait history of this individual. And what we observe is this picture. That means here you have the genealogy of all individuals in the center of the distribution capital F at time t. And if you consider the trait history, you see that these individuals here at time t are not issued from individual in the center of the distribution at time 0, but they are all issued from very maladapted individual at time 0. That's important to remark, especially for people in agriculture or so on. If you destroy the maladapted individual at time 0 after a certain environmental change, you could be bad, since you see that really here maladapted individual at time 0 explained, in fact, the well-adapted individuals at time capital T. And our questions are here. Are we able, now we assume that we observe individual at time t, we pick up at random one individual at time t in this population, are we able to find the trajectory for this individual describing in a reverse time, describing the path, the trait path of this individual until its ancestor, and to find in that way the distribution of the ancestor. And what we will see is that, in fact, the fact to choose an individual alive at time t at random here creates a sort of bias in the observation, since remember, in our population dynamics, we have birth and death. And here, if we choose an individual alive, that means that since it's alive, we have to bias the population by the fact that it is alive. Okay, and so we will see how it can be described in a probabilistic framework. Okay, so now I come back to these ideas I have introduced. So remember, we have assumed that K is large, that the initial condition is close to the equilibrium F, and then we will replace the total mass nu K, the total mass of nu K. So that means it's the number of individuals at time t divided by K, and we replace it by the total mass of our equilibrium, capital F, and that we call, which was our lambda. Lambda, remember, it has a value depending on sigma and C. Okay, so that by replacing the mass of nu K by lambda, give us a new process, and we can construct on the same probability space than nu K. That's why I speak about coupling. And this new process, I called it ZK. And the main difference is now that ZK is a usual branching diffusion process with independence between all the individual paths, because we in fact, we replace this interaction term by a fixed deterministic real value, in fact. And the coupling is described by this mathematical property, is that if, since Zk is also a measure valued process, that if we integrate any test function phi with respect to this new process, and the difference between this quantity and the same one with our previous process with interaction, then the two integrals are close when K is large and uniformly on time and finite time interval. Okay. And so we will now study this process instead of this one. And here, since it's a branching diffusion process, we have beautiful properties for this process, and a lot of tools can be used. And in particular, we know, because of the independence of individual paths, and also all these paths have the same law, that we can study the process with only one initial individual, what we will do now. Okay, so so we take this new process, so with the non-linearity replaced by lambda, and we assume that we have a unique ancestor with trait x. That means that the measure valued process, the initial measure value is Dirac measure on x. And the first thing we can observe is that if we want to know the law of this measure valued process Z, I forget K for the moment, it can be described through an auxiliary process, YT, which here is just the Brownian motion, the mutation Brownian motion drifted by the environment. Okay, and so you have this process, but here you have not the law of this process, but you see here you have a multiplicative functional, which is the exponential of a term which only depends on the growth rate, 1 minus, so it's a birth rate, and here you have the death rate, y square over 2, plus lambda, and remember that the ecological part of our process has been replaced by lambda. And so you can describe the law of the process ZT from this individual, unique individual with trait X by an auxiliary process one-dimensional process, very easy process here, YT, initiated, issued from X, okay? And in particular, if we consider the mass, the total mass of our process ZT, that means we take phi is equal to 1, then we introduce this function depending on X and T, mt of X, which is the expectation of our total mass integral of ZT, then it satisfies, it's equal to the expectation of this multiplicative functionals of the exponential of this quantity depending on y. And of course, it's easy to prove by standard arguments that it's a very smooth function. And we can do a lot for this function here because the process is very simple. And it's by Fernand-Kac formula, we can prove that it is solution of this new PDE. And we can, by probabilistic arguments using Girsanov transform, we can explicitly compute the function. So whatever the formula, it seems to be complicated, but it's easy to understand. And you find here the Gaussian law we have already observed through the function capital F and the environmental effect here. So we have an explicit formula for mt of X. And we can also prove that if we integrate this function through the measure, the equilibrium measure f of x dx, it's also equal to the mass of f, and that is 2 lambda. Okay, we have a sort of stability. And for people knowing this Perron-Frobenius theory, it's an infinite dimensional point of view of the same theory. Okay. And so we have this auxiliary process, and now we would like to generalize this point of view and to exploit this point of view for our questions. And so I, sorry for the very naive picture, but it's my branching diffusion process. So it is issued from one individual with trait X. And so you have a branching diffusion from this individual until a point. So at trait 1, you have a reproduction event, and now you have 2 individuals which are independent one from the other, both moving through the Brownian motion, sigma bt, and then another time you have a birth event here and here. They are not exactly at the same point since all are independent. And you can also have days. For example, here you have a death event here also. So at time t, you have a certain number of individuals, and you can. So here I observe I have a distribution. So of course here I have only 6 individuals, but at time t, imagine you have a distribution of individuals, and you could ask, what is, given this observation, that is my individual distribution at time capital T, what is the distribution of the traits of the ancestor of my observed individuals at time small t, or even what is the total path of all the ancestors responsible of my observations at time t. Okay. And we know that the total path, the law of this total path can be described by the law of the trait values at different time before capital T. And so we can generalize the formula we have seen previously in the previous slide to by studying. So we, as before, we have our observation time capital T, and we observe, instead of observing just things at time Paul, could you answer me?
I'm sorry. I don't know. My Zoom quitted, so I didn't see you for a while. Sorry.
But do you see my screen or not?
Now I just see you, but not your screen.
So I have to come back, I think. Well, okay.
Yes.
Ready? Okay, so I continue. It's okay?
Yes.
Okay. And so we have a formula describing all this past history, but what is the main point here is that the description of this law in the past of all individuals is based on a unique one-dimensional process Y, okay? And that's the main very important property of branching processes that we exploit here, okay? So I can, okay. And now I arrive to the one of the main results of this talk is that, remember I said I want to pick up at random an individual in my population at time, in my observed population at time capital T. That means that uniformly on the total number of individuals at time capital T, that means the total number is nkt. So I choose uniformly at random an individual. So I consider 1 over nkt, and I choose an individual. I consider its historical past. Okay, so I consider all the values of the trait for S less than T, the trait of the ancestor, the successive ancestor of the individual I. Okay, and I can prove that this quantity is equal to the expectation of a new, so it's a law of a new process which is constructed. So it's an inhomogeneous Markov process, but whose generator can be obtained from the generator of the drifted Brownian motion. So these formulas are well known in the world of branching processes. They are called many to one formulas, and so you see that gives you the law of the historical path of an individual taken at random at time t. Okay, and it's given by this generator. So now I will finish the talk just by make computation, because I remember we have computed explicitly this function mt, and you will see that we will obtain very simple thing. So we can prove using this mt, we have an explicit formula for this process, this inhomogeneous process y tilde t. So y tilde t, what is if that I take at random an individual, for example, the pink one, and I give the trajectory from x to this, the trait trajectory, the law of the trait trajectory from x to this pink trait here, okay? That's what describe my process y tilde t. And because of the formula I gave for mt of x, I have this equation for the stochastic equation for y tilde t. You have a Gaussian term here, it's a Cameron-Martin integral, and plus some very specific drift term. So what is interesting is that, in fact, for any t, it's a Gaussian law. It's a Gaussian law. And you have here exactly, but it's inhomogeneous. So, of course, the mean and the variance are depending on t, on small t, and you have the exact quantity. So you can write the density of y tilde, it's the Gaussian variable, and you have also an expression for the derivative of the density with respect to y. And that's the main point on my last slide, is that because we can compute, we can also compute the reverse time process of this y tilde t. That was the question we had in mind at the beginning of the talk. we know, and we use some known result by Osman and Pardue, allowing to compute the time reversed diffusion from this diffusion y till t. And if we make that, means that we return time instead of considering time in forward direction, we consider time in backward direction. That means the time will be from capital T to time 0, and we make this time change from t. We consider capital T minus small t. And if we make this change, and that's very amazing, is that the new diffusion, the time reverse diffusion of the process yt, is a very simple Ornstein-Uhlenbeck process, and which is homogeneous and independent of the observation time, capital T. And it's given by this quantity. It's just sigma times dBt minus xt dt. Very simple stochastic process. And so, of course, the independence from the observation time is due to the fact as we consider the underlying framework is an equilibrium framework in the moving environment. But what we are saying is that if we pick an individual at random, the trajectory to go from the individual trait at time t to the trait of the ancestor follows an Ornstein-Uhlenbeck process. And of course, we understand on this Ornstein-Uhlenbeck process that the main direction of this drift is to go to 0. Okay, and so that's why we have 0 with the red line here is the trait 0. Okay, so I have finished, and so you have all the picture here, and thank you for your attention.
Yes, Sylvie, thank you. So I don't know how to make some applause, but anyway, thank you very much for your interesting talk. So I would like if some people want to ask any question, we have some few minutes for this. For my own, I wanted to ask about the coupling, because in fact you couple with fixed functions. So it was on page 15. You have a coupling in page 15, and this coupling is for a fixed function. Do you have even some coupling which is uniform with respect to some classes of functions? Because I think this should be useful in order to have some statistical applications.
From which function do you speak? I mean,
the function phi in the.
Because here phi is just a test function. That means the coupling is between the two measure valued processes.
Yes, I understand, but even
yes,
can you make something uniform with respect to this phi or not? Is there a way to do that?
The uniformity in phi, you mean?
For some classes of phi.
I don't. In a certain class of function, yes.
For sure. Okay, yes, for sure, not for.
Since we have just point measure valued, of course, after you cannot put. I suppose you imagine some some class of smooth function or something like that, because here you have just point measures. You see, so the test function can be. But
yes, okay.
Well, I have to see.
I don't know if there are.
That, of course, it's
thank you.
Bonded. It's easy. After that, no, I think that no, except if you have bounded functions in a class of function with a bound, because if not, you see, since you have only point measures here, you cannot do. Of course, if you would have here the solution of the PDEs, you could do many things, but here with the measures.
Thank you. Maybe Eric wanted to ask a question.
Yes, thank you. Yes, I may have a question. It sounds like you have a variance parameter sigma, which plays an important role. In my field, which is financial econometrics, we like to consider what we call conditional heteroscedasticity or stochastic volatility. is there any reason to think that the parameter sigma could be time dependent and stochastic?
So sigma, here I took a simple model with this Brownian variability, which is relatively standard in evolution, but you can imagine very different kernel, and usually we prefer jump kernel. But yes, of course, you see all these population dynamics can also be in a certain scale summarized by Feller diffusion, which is not so far for equation for your.
Yes, typically at the end, instead of Feller Stanley-Beck, you could expect.
Here you can, in fact, this model is simple. You can imagine a very, very a more complicated system. Of course, sigma usually should at least depend on x.
Yes.
Because that's one of the points when because it corresponds to mutation of the individuals. And T, yes, why not? You can, I think that if you go really inside biology, all things are so complicated that depending on the species you are studied, you can add very different properties.
Okay.
But also in this model, it's very naive to put such environment. I would like to add at least dynamics on the environment, stochasticity on the environment, but I think that it will be open to very difficult mathematical questions. I think it's the beginning of some.
Okay.
Some work. But of course, you can generalize this. But I'm not sure that it will. Of course, you hear what was interesting in this case, that we can make the computation until because we have the exact formula for this function m mt of x, which is the bias of in our problem. If sigma depends on t, it will be more complicated to compute, certainly.
I am sorry, because we need to keep a very straight schedule, and I think that the next orator is waiting. He also asked questions, so maybe we should go to the next speaker and ask Eric Renaud to begin. Would you do you mind? So thank you very much again for Sylvie, and please, Eric, go ahead.
Okay, I try to share screen. What is going on? Okay. Okay. Is it okay, Paul?
Yes, perfect.
Okay, so thank you for the invitation. So I'm going to talk about causality, as you said, and in particular the role of which is several meanings of lag augmentation. Okay. I will organize my talk in two parts. I will first talk about testing for Granger non-causality. Granger non-causality is something popular in econometrics, as you may know, and the originality of the point I will make is that it may be relevant to consider it at different horizons. I have a second part where I set the focus, instead of testing for Granger causality, I set the focus on measuring causality. I will see how much I have time to do on that, but okay, this is the idea. Okay, so first, testing for non-causality. Okay, so I will refer for the story of causality to different horizons. The beginning of this research agenda started with a joint paper with Jean-Marie Dufour a long time ago. So basically the idea is that you will be interested in two processes, X and Y. So typically you're going to ask whether Y is causal for X, but we are going to see that additional environment, Z, may play an important role if you think in terms of different horizons. So basically the definition of Granger non-causality is to say that Y does not cause X if when you know the past of X and the past environment of Z, then Y does not help to forecast X. This notation minus omega bar is just to say that you can go until minus infinity if you play with stationary processes. And if we play with processes with unit roots, you may want to start from some initial date. Okay, so it's a kind of general notation. Anyway, so the question of causality at horizon H is the fact that now we consider what is the improvement of forecasting when you forecast at horizon H, okay, which has not been so much studied in the literature. And so that's why help to forecast X, given some environment where you have some also variable Z. Okay. In particular, to be quite general, you can think about an infinite autoregressive representation of your joint process. I stress that this infinite autoregression may include unit roots. So I do not assume stationarity. I just assume some simplicity of my talk that the variance of the innovation process is not singular. Okay. And then in this context, you can compute from this autoregressive representation, you can compute forecast at horizon H just by iterating the autoregression, but of course. So you will introduce some kind of new autoregressive parameters, which you grab how do you forecast at horizon H, you know, from G equal 1 to infinity. So knowing on the path from T minus 1 and so on. So forecasting at horizon H, we'll introduce some autoregressive parameters at horizon H that you can easily characterize recursively like that. That to say you have directly your initial autoregressive parameters plus all the combination you may imagine of causality at smaller horizons and going through the autoregression. Okay. Among macroeconometricians in particular, which I'm not, but I try to understand what they do, there is something which is popular, which is called impulse response coefficient. What do? They actually just look at the kind of Vold representation of the process. So basically, the lag polynomial psi, it is a matricial polynomial, of course, is related to the autoregressive polynomial pi by the fact that it is the inverse of the other. And so this, you get the process as function of the past innovations, right, as in a Vold representation. It is exactly the Vold representation in the case of a stationary process. But I do not preclude non-stationarity. Anyway, just by the fact that the two polynomials should be invert of the other, and this is the identity matrix of size M, where M is the total size dimension of the process, you have this recursion on the parameter psi in order to get identity when you multiply each of them. Okay. And something interesting to realize is that this recursion, which is of course just algebra on this equation, is tightly related to the recursion I have written a minute ago in my famous slide on the autoregressive parameter at different horizons. If you look at them, there is kind of a similarity. And let me be more precise on that. If I look with only one lag, the autoregressive parameter at horizon H, applying my recursion gives me this formula that I can rewrite like that with this convention. And I suddenly realize that this forecasting parameters at horizon H, but just with one lag, exactly coincide with the so-called impulse response coefficient, which are so popular in macroeconometrics. It's kind of funny that this identity, which is just simple algebra I have just explained, I gave the proof just to show you how simple it is. It is something that we have said with Dufour in 1998. And it sounds like it has been completely overlooked for 22 years, because it is only very recently that this, in a working paper from Princeton, these two young guys from Princeton, I've written a paper saying local projection and VAR estimate the same impulse response, that is to say, what I just say, is that if you compute your impulse response psi from your autoregressive parameters by solving the equation, they are nothing but what they call local projection, which is this forecasting at horizon h. That's the funniest thing is that there is this new terminology, local projection, that we did not use with Dufour, but just a way to describe what we call with Dufour regression at horizon h when you forecast the process at horizon h. Okay. So we have this identity. So of course we estimate the same thing, we agree on that. And I would like to elaborate further. Number one, I would like to stress that in order to understand that y does not cause x at horizon h, you have to look in the autoregressive coefficient or the impact of y on x at horizon h, but not only with one lag, but also with two lags, with three lags, and so on. This impulse response coefficient so popular do not tell you the complete story, because they just tell you this causality at horizon h with one lag. Okay? I don't know whether the are clear. You know, it's kind of funny to say, I'm interested about causality. So when looking at this equation, I would like to see to what extent y has an impact on x. But this impulse response coefficient, look for this impact, they just look with one lag. They just don't look at the lag, the higher lags. Okay, so they miss something. You may say it's not a big deal because in real life, we don't have infinite autoregression. But the first point I want to make is that if you have autoregression at order p, sure, this forecasting coefficient at horizon h are zero beyond p, but you should consider them not only for j equal 1, but j equal 2 until p. Okay. Second remark, if you really want to characterize, you know, what we had in mind with Dufour in particular is that it's not enough to say that you have no causality at horizon 1, because maybe through indirect causalities and so on, when you go further, you may create some causality. So we say there is no causality up to horizon h to say there is no causality at horizon 1, 2, 3 until h. And basically to get it, you have to look not only at the initial autoregressive coefficient, which characterize causality at horizon 1, but you have to multiply all this kind of coefficient by this impulse response coefficient, where I'm talking about z. So basically, what is the idea? If y is a cause for z, and z has itself, through the impulse response coefficient, an impact on x, you will create what we call an indirect causality from y to x, which goes through z. And you have to look at all these products. So this terminology of local projection has been introduced by a macroeconometrician whose name is Jorda in 2005. And the funny thing is that in 2006, and we are not aware of this paper because, as usual, when it is published in 2006, it was a working paper. In 2003, we are doing exactly the same thing, but we are not using the local projection terminology. So basically what we say is that why it is interesting to go through local projection is that when you want to estimate these parameters, they are polynomial function of VR coefficient, relatively complicated polynomial functions. And you want to testing for causality, you have to look at these parameters. And as I've seen before, it means also that you have to look as restriction of non-causality, which are something like that. And I don't know whether you have ever met that, but it is a very simple issue. When you want to test that the product of two parameters is 0, it is not an easy task. And why it is not an easy task is that when you look at the rank of the restriction under the null, you may have only one of the two parameters, which is 0, or both of them. Meaning the rank of the Jacobian matrix is not constant under the null. It can be either 1 or 0. So this is just a product of two univariate parameters. But you may imagine with the product of such matrices, it is a mess. Meaning that if you want to just use the standard inference on your vector autoregression to test that, you will be in trouble because the standard asymptotic tests do not work due to this rank deficiency. We have tried to do that actually with my colleague Dufour and Zide Walsh. This paper you can find on the web. to characterize wild tests when restrictions are locally singular. We actually show that the world test statistics has always a limit distribution, but it is not the standard chi-square. And the problem is that, of course, this distribution is not constant under the null, which make hard task to devise adaptive strategies. So this difficulty of inference is the motivation for this so-called local projection. What local projection is a terminology introduced by Jordan. With Dufour, we say pH autoregression, where basically you directly work on this regression equation. Basically, you forget that behind these parameters, there is some VAR parameters. That is, this guy are function of these VAR parameters. Of course, forgetting that, overlooking that, you waste some information, and so your inference is not going to be efficient. But at least it is simple, because you realize that OLS on this equation works. Why does it work? Because here you have a moving average process, but all before this guy. So OLS is consistent for these parameters. It's not efficient, but it is consistent. So this is basically the reason why these local projections have been popular since 2005. Because otherwise, if you had to use a complicated nonlinear relationship between this guy and the autoregressive parameters, you will have to use the Laplace theorem, and this function present, as I said, we have some singularities in the Jacobian and so on, so it would be a mess. Okay, so you give up efficiency for the sake of simplicity. Okay, a few things I want to say about this local projection for testing for non-causality. Number one, due to the indirect causality I have pointed before, if you really want to check that y does not cause x at all horizons, this is an if and only if, you have to check that y does not cause x at horizon 1, 2, 3, and you should not stop at p. You should go until p m3 plus 1. What is m3? It is the dimension of z, the environment, because through the m3 component of z, as I explained before, any kind of indirect causality may go through. So even if z is dimension 1, you have to go to p plus 1 and not only p, okay? So it is a kind of first lag augmentation for testing for causality at all horizons. The order of the VAR, p, is not enough, okay? Another lag augmentation, which we have introduced in this paper with Dufour and Pelletier, was the following. You know, when you know that you have a VAR of order p, you are going actually to run a regression on p plus 1 lags. Why doing that? The issue we had in mind with Dufour and Pelletier was to hedge against unit root. Well, you know, when you consider macro variables like GDP as this kind of thing, often there is a unit root, okay? And they are co-integrated and so on, so it's not so easy to get rid of these unit roots. There was a seminal paper by Simstock and Watson saying if you want to get rid of unit roots with simple procedures, just add some useless lags. That's even if you are convinced that your process is Markov for the p, put p plus 1 lags. And there will be kind of miracle that the additional lag, I'm going to explain why in a minute, is going to protect you against non-stationarity. So basically, this has been put forward for testing on vector autoregression. And basically, with Dufour and Pelletier, we had extended this argument to local projection. That is to say now, okay, instead of looking at regression of order p, I will look at regression of order p plus 1. That is actually, as I told you, this work has been very recently revisited by Preston guys. And there's another paper by this guy, Montiel and Plagborn-Moller. The title of the paper is Local Projection is Simpler and More Robust than you think. And there's a few arguments I put forward that I want to convey to you because they are quite interesting. You know, I nicely provide just a very toy example. You just take a univariate autoregression of order 1, which is, of course, not my focus of interest today. But I'm sorry, I have some issue. You just take a autoregression of order 1. And you look at this forecasting at horizon h. So, of course, you know that this guy in this case is just pi to the power h, but I forget it. Because once more, I don't want to use the relation between this guy and the underlying autoregressive parameters. Okay, when you realize, when you write it like that, in that you plug you replace yt by pi yt minus 1 plus epsilon t, you realize that this forecast equation can be rewritten like that, where you have epsilon t and yt minus 1 with one pi, with an additional pi. Why is it interesting to look at it in this way? Is you can relate, because this is an infeasible regression because you don't observe epsilon. But you can relate it to a feasible regression, which is making the regression on yt and yt minus 1. What does it mean? You have a regression for the 1, and you make a regression on 2 lags. So you have a lag augmentation. And by a simple Frisch-Envoy argument, you realize that doing OLS, this infeasible OLS on these 2 guys, in terms of estimating this guy, you get the same estimator that if you do feasible OLS on these 2 guys, right? Because the difference between yt and epsilon t is something which is orthogonal to that, so does not play any role. So basically, this is the intuition why this lag augmentation is so fruitful, is that it is as doing this infeasible regression on this guy. And what the nice thing with this guy, it is a white noise, it is serially uncorrelated, it is stationary. So you have basically, if there's a unit root issue, you have killed the unit root issue that you may think you have when you make yt. Okay. So the first benefit, that it is the idea we had with Dufour and Peltier, was edge against unit root. What Plack-Barmoller and co-author have stressed, that's a second benefit, which is edge against serial correlation in this guy. You remember this guy is a moving average of order h-1, making OLS even more inefficient. But you realize that you don't care about this serial correlation. That's kind of miracle, because when you do OLS, the OLS formula, right? X prime x minus 1, x prime y, which matters is not really y, but it is x prime y. With this guy called the regression scores. And you can show that the serial regression scores are actually serially uncorrelated. At least if you are ready to maintain this weird assumption, is that the innovation epsilon is not only a martingale difference sequence to get central limit theorem, but it is also a martingale difference sequence with respect to the future, if I may say that. These assumptions I maintain. I'm glad to get, I will be glad to get comments from you, because this is something which has been written very recently, as I said, and it is not clear to me yet how restrictive is this assumption, okay? You assume that epsilon t has a zero conditional expectation, not only towards its past, but also towards its future. So I don't know whether that's something like time reversibility, but something which will be worth considering. Okay. Now, maybe I should stop before moving to the second part. Is there any clarification question at this stage, or may I move on? Okay, so let me move on. So I move on to my second part, which is about causality measures. This is something which has been pointed out for the first time by John Gewicki in 1982, saying, okay, that's fine to test for non-causality, but in general, you will always find some causality. The question is this causality economically important or not? So how can we measure the actual degree of causality? John Gewicki has done that only for Gaussian processes, Gaussian autoregression processes. With Goriot and Montfort, we had extended that to any kind of processes, for instance, qualitative processes and so on, by introducing a general concept of Kullback causality measure. I have revisited more recently this work with a student, because I realized that in this former work, we had kind of overlooked the fact that when you test for causality, you should not be misled by some Markov issues. That is to say, under the null of non-causality, you have some Markov properties which are not fulfilled anymore under the alternative of causality. So if you go farther than testing, but you really want to measure causality, there is some complications that basically we have studied. Okay. To of causality, maybe they are more familiar, less familiar than with Granger, because maybe it's more something that communication are using. So-called Sims non-causality. Chris Sims has the following argument, which is maybe not completely straightforward, so I will say it just slowly. Actually, it's not straightforward for me. I have always to think about it. If you want to think that Y does not cause X, that is to say X is really exogenous, it means that, a natural way to test for causality would be to say, if you want to test that X exogenous, just regress X on Y and see whether it depends on Y. But what Sims is doing is kind of reversing the point of view, saying if X is exogenous, when you make a regression of Y on all the paths of X, not only past and future, past, present, and future, the future of X should not show up, should not be significant in the regression, because if the future of X is significant, it means that it incorporates something about Y, so somehow Y is causing X. This is the way Chris Sims is thinking about causality. Okay. Okay, it is interesting to think about measuring this causality in the sense of Sims. To do that, I will be more parametric than I've been so far. I will write a model with a likelihood function. I will say that Y does not cause X in the Sims sense, so Y LCS X. If when you look at the density of Y, given all the X, all the dates, past and future, capital T is the last date of your sample, and the past of Y, basically the future of X is useless, is irrelevant. You have only the past and the present of X in that. Okay, this is what Sims call non-causality from Y to X. Okay, how can you measure that? It is something we have done with Gorion and Montfort. You will say, look, I have this joint density function. I put a 0 to say it is a true one, the data generating process. And now I have a set of density function where Y will not cause X. And what I'm doing, I'm looking at the Kullback distance between the true one, the DGP, and any possible F where there is non-causality. I'm minimizing this distance. I'm minimizing this distance over F. Basically, give me the kind of distance between my observed process and the non-causality assumption. So it is a measure of causality. Okay. This measure of causality is non-negative and is 0 if and only if there is non-causality. So it's kind of a distance. Of course, there is no such thing of symmetry or whatever, but it's kind of a distance. And the funny thing is that you can actually compute it explicitly. When you have minimized over all the positive F, possible F, you end up with actually the true F0, but the true F0 that you have written as if there will be no causality, that the future of X will be non-relevant. So the Sims causality measure is just to say, compare the true density and the density you will use if you do as if there will be no Sims causality, the future of X will be irrelevant. So I think it's quite natural. Okay, now what is the connection between Sims and Granger non-causality? If you do a very elementary decomposition of the joint density given, basically when I look at this guy, I'm basically thinking about the initial condition of my process, right? So if you look at this, I not maintain any Markov assumption or stationarity assumption or whatever. So if you look at this conditional density given the initial values, basically you realize there is two parts. Because you can always factorize the joint density like that. So basically, you see that this is talking about Sims. To what extent the capital T is important, we could stop at T. You realize there is a small remainder term, which is basically, we have called it initiation, it has not been considered before us, where you think about to what extent the initial value of Y are useful to understand the distribution of X. So basically, in this decomposition, you see that you are talking about initiation, about Sims causality. Okay, so initiation is not something very subtle, so I'm going to be relatively fast, but you can measure it, the impact of initiation. Same thing by looking at the minimum Kullback distance. And basically, you end up with the initiation measure, which is basically comparing this and this where the initial value of Y will not be used. Same thing, it is non-negative, it is 0 if Y does not initialize. Okay. The point is that often people have overlooked this term, saying that it was negligible. But if you think about it, there is no reason to be sure that it is negligible, even with stochastic processes, with stationary processes, even when t goes to infinity. Maybe this guy is not negligible. Okay. Now, if you add these two guys, Sims causality measure, initiation causality measure, you end up with a guy that is not with G, like Granger, because basically you realize that it is a Granger causality measure because it compares something like that with what you will do if y does not cause x in the Granger sense. You remember, y does not cause x in the Granger sense. It means that the past of y does not help to forecast x, so it is basically this ratio. So same thing, this Granger causality measure really characterizes Granger causality. And you realize that it is zero if only if you have two things, not only you have non-causality in the sim sense, but also non-initiation. Okay. So this is something that has been said in the past, but people did not characterize it in terms of measure, is that if you want to relate Granger and Sims, you have to get rid of the initial condition. This is basically what I did. Okay. Now let me go to the for my last part of my talk to this point I want to make between the relation between causality and Markovianity. When people want to do inference on this thing, of course, they will be tempted to consider that they have autoregression of order P. You may know that in econometrics, in macroeconometrics, much with ARMA, vector autoregressive moving average. They like vector autoregressive because basically you can do LS and so on. Okay. So typically, as I said, this has been initially by Gewicki for Gaussian VRP. Then some French team have worked on qualitative panel data for the conjuncture survey of INSEE. And it has been also kind of funny recently rediscovered by people in physics. You know, you have some, if you look at physical review letters and publication in physics, I'm not used to do that. They call about transfer entropy, which is basically the same Kullback measure. Okay, anyway. If you want to use the fact that you know now that jointly X and Y have Markov order P, it means, of course, that here I can look at only at P lags, here I can look only at P lags, and so on. However, I stress in red that here I cannot look only at P lags. Why I cannot? Because when Y does cause X, even though Y and X are jointly Markov for the P, of course, X in isolation in general is not Markov for the P himself. So I'm not allowed to stop at T minus P. I have to go until the infinite path, or at least all my initial values, if I look at this causality measure. The funny thing is that this fact has been ignored by Goriot, Montfort, Renaud, and by Schreber, and all these guys. How can you understand this mistake? Because I call it a mistake, right? And I'm allowed to say that because I put myself in the mistake. It is a mistake because people have made a confusion with testing. When you test for non-causality from Y to X, and you know all the critical region you compute and so on, you are focused on the property under the null. Under the null, that Y does not cause X, X becomes himself Markov for the P. So it's correct to see it as a Markov for the P. But precisely the point of measuring causality is not to assume that Y does not cause X, right? So there is no reason to stop the path for X at T minus P. Okay. So you have a kind of another motivation of flag augmentation. You should go at least to T minus Q, with Q significantly larger than P. And this is basically what I'm going to consider. I would say, let me work as if the process will be Markov for the Q larger than P. That's to say, I know that the P is a sufficient order, but P is going to be misleading when I will look at X in isolation. So I will look at Granger causality now when I put Q as number flag. This measure of causality. Okay. Basically, what it means is that it's my measure of causality. Now I have a T minus Q in terms of T minus P. Typically, of course, it's just an approximation because I should take Q equal to infinity in general. Actually, if you look at the difference between the two, you have another measure, which is a measure of Markovianity. So you look to what extent you are wrong, and assuming for X that it is Markov for the P, while it is not Markov at all, for the Q, sorry, while it is not Markov at all. Okay. And basically, you have against causality measure, and what you can see is that if you do like Gourio-Montfort-Renault or Schreiber and so on, you just put P lags, you overestimate the Granger causality measure. With more lags, you will less overestimate. And you should actually take an infinite number of flags to get. Of course, there is no causality, no Granger causality. All these measures are zero, or there is no issue. But lag augmentation becomes necessary when there is causality, and you don't want to overestimate the Granger causality from Y to X. Once more, sorry, the source of overestimation is Markovianity, not Markovianity. That is, as I said, this Granger causality measure is the true one plus a measure of non-Markovianity. You make a confusion between the two. You may wonder whether this effect is important. I have played to give you a small numerical illustration, Bavarian process. Typically, there is a change of basis, in this diagonalization, but basically, you have a very strong coefficient on the diagonal. So you can see about lambda 1 as almost being the persistence of X and lambda 2 being as almost the persistence of Y. Okay. And rho is important, the correlation between the relations. Okay. So what is going on? If you look at Granger causality of horizon Q, when you increase Q, not horizon Q, sorry, where you think about Markov for the Q. When you increase Q, as I said, you downplay the causality measure because basically this overestimates causality, and the right causality measure is this one. You may say the difference is not that much a big deal, but look at another example. Yeah. If you assume Markov for the one, you think you have this amount of causality. And suddenly, when you put larger lags, you realize that there's actually no causality at all. What is the trick to get this extreme picture? Is that I put a correlation coefficient between the two inhibition of minus 0.99. So what is the trick? Is that as soon as you have observed, you have two lags of X, since X is so correlated with Y, basically you have incorporated the information coming from Y, and so you realize there's no causality anymore from Y to X. So this number is highly misleading. Once more, the point is that sure, XY gently Markov for the one, but you should not consider X Markov for the one, what basically you do when you do that. Okay. This has consequences for statistical inference. I will not be too long, but basically what Guy-Wiki and we had done with Gourio-Montfort, overlooking this difficulty of a number of flags, you have maintained the assumption of Shari Markov, and we had, as we remember, we had the correct number of flags in the X equation. Okay. And we just replace it by sample counterpart, and we replace Kullback causality measure by sample counterpart. You have basically, up to some non-significant differences, you have basically a likelihood ratio test. So it's a likelihood ratio test for causality that you base on the Granger causality measure. But as I said, this Granger causality measure is misleading. Okay. So this is likelihood ratio test, so you have standard chi-squared and everything works easily. Basically, you end up with comparing the determinant of the autoregression with and without causality. Okay. The point I've put forward that you should do lag augmentation suggests to do something else. This is something I have discovered at this time in the literature, that some people are working with asymmetric vector autoregression or asymmetric Markov. Basically, what they do, they say, maybe we don't want to put the same number of flags in the equation. Say we put more flags for the X variable than for the Y variable. Okay. They put the same thing in all the equations to keep the advantage to do LS and so on, but they put more lags in the X variable. Okay. Something which is popular, which was actually the initial motivation of SIMS, is to see the impact on money supply on output and conversely. So basically, you put 6 lags for the money supply because it is a large number of lags for the candidate exogenous value. Okay. Now, even this is not very satisfactory because you kind of sure it's a good idea to put more lag for X, but if you put more lag for X, it is typically to get rid of the case that Y is not written anymore. Okay, so we have more set the focus on another approach, which is asymmetric var also, but looking now that when there is no causality, this Y has no impact. It is in this case that you put a large number of lags for X, and it is not necessary in the Y equation, it is not necessary when there is causality. This is, I guess, intellectually more satisfactory. There is a price to pay for that, is that now the null hypothesis is not nested in the general model. So it is typically what econometricians call non-nested hypothesis. And one popular solution is the Cox likelihood ratio test kind of thing we have done. Okay, so basically meaning that now you're basically what you are testing is based on this causality measure. Okay, okay. Let me briefly conclude. So we have been led in this last story on looking at testing for non-nested hypotheses. It has been criticized in the literature because, generally speaking, I mean, non-nested hypothesis, because to some extent, there is no kind of symmetry, no way to think about it. You know, it's not an Neyman approach, right? Because when you reject a null, it tells you that you reject a null, but it does not tell you that the alternative is the right thing to consider. So, because maybe if you test the other way around, you will also reject the alternative. Okay. So basically, what should we choose? To some extent, I guess it depends what you want to do. If you just want to do forecasting, you can work with the standard VRP model and nested hypothesis. No problem. You are just in a descriptive way try to characterize the model which gives you the best forecasting, the best stuff. Now, if your question is really testing a theoretical question, you know, you have some theory in mind, you think that Y should not cause X, then in this case, I think you should use our approach of non-nested hypothesis, because in this case, you are really an asymmetry between the null and the alternative, and this lag augmentation will make sense. Okay. So you may have noticed that I had this concern with Granger causality. I had not this concern with Sims. That is to say, you know, if I come back very fast to my formula at the beginning, you realize that this theory that I should put an infinite lag was coding with Granger and initiation. With Sims, I was in business because the way it works always allows me to work with T minus P. So what does it mean is that even though Granger causality, I guess, is much more popular among statisticians, there is some benefit of using the Sims approach, because basically, in the Sims approach, you don't have this non-nested hypothesis at work. You properly take into account the Markovianity issue. So to an extent, it's the same way you like non-nested model that you would like to think about a general model to make your test. Sims concept of non-causality play a similar role to that. That's both effect. Okay. Finally, because in the title of my talk, there was focus on different horizons, I have talked about different horizons only in the first part of my talk, not the part of causality measure. This has been done to some extent in the literature by Dufour and Tahamouti. However, they have to play with complicated, even more complicated nonlinear function of VR parameters, so they have to do simulation-based inference for this causality measure. To some extent, the research agenda now will be to take advantage of the recent progress on local projection. We have shown that it must simplify inference on causality at different horizons. To take advantage of this approach also for causality measure, where basically you have to take into account indirect causality, as I said, when you are at different horizons. Some causality may go directly through Z, and this should be taken into account in your causality measure, and inference should be simplified by this local projection. So to some extent, lag augmentation will show up now for 3 reasons. One, because your local projection should be lag augmented. Second, because you should consider causality at horizon larger than P. And third, as we have said, because you should take into account of non-Markovianity of X in isolation. Okay, so I guess I will stop here. Thank you.
Thank you very much. So I'm sorry. I thank you first for the talk, for this nice talk. And I really don't know if we have time for discussion.
I'm sorry, I forgot the 5 minutes left.
Yeah, I wrote you a message, but
I'm so sorry.
difficult to see them when you present. So I suggest, in case there are questions, to set them directly here or with email or even on the YouTube channel. Is that possible? So that I suggest so that you quit the sharing screen and that we come to the next talk. I see already the next speaker.
Okay, let me try to quit it. I hope I will manage to do that.
I think it's
okay. Yes.
So thank you very much, and thank you for coming. And now thank you to Lionel to give a talk, and that's really a pleasure to welcome him.
Okay, so thank you. Can you hear me?
Yes.
And for the full screen, is it okay?
Yes, it's okay. For my part, I see it. I will cut my sound because I don't want to interrupt you. Okay.
Oh, okay, perfect. So first, thanks to Paul for organizing this conference, which is quite difficult to organize, and also to bring us together to this interesting project around ecological problem and dependence, in particular time series analysis. So I am not specialist at all of ecology, but I am interested in a general problem in time series analysis. Some of the issues that I will discuss here will be quite well connected with the previous talk of Eric Renaud. I am interested in a general problem which is to get a mathematical framework to study with some statistical procedure, some models, some nonlinear models, for which you can include some exogenous regressors, which is a problem that is not very well studied, in particular to obtain some conditions to get some stationary paths, and then to apply some standard classical procedure. But to play the game for this link with the ecological problem, I will try to present as a kind of motivation this data sets, which come from a platform that everybody knows, I suppose. It is a Kaggle, and it proposes some competition around the data, where the problem is to forecast, to predict some quantities. So here the problem was to predict the weekly number of dengue cases in San Juan. So you have this original data set here, and they give also additional information relative to other quantities, such as the humidity, the average temperature, and the vegetation index. And you have also other type of information that I will not discuss here. So what is important here is that we want to measure, to predict or to measure the importance of some meteorological quantity on the outcome. But when we see these very large spikes at some special dates, this will be not probably explained by all the additional time series. So it's probably important to make an hybrid approach on which you can put what we will call the exogenous quantities and the endogenous quantity, which will be the lag values of the response. So, and this is the starting point to motivate a bit the studies that I will present here. So if YT is the time series of interest, so we call XT the exogenous covariate. So we'll precise the sense of this exogeneity. We want to explain or predict YT using the past values of either the outcome or the exogenous time series. The main problem is that when we try to study theoretically the properties of some models, in some classical models in which you can include exogenous regressors, so the theoretical study is quite recent. In practice, of course, you can always put some exogenous regressor in some dynamic, but the statistical guarantee are not always easy to obtain. In particular, if we are interested in getting some condition for getting a stationary solution in the equation that define the model. So I will go back to this point after. So you have some contribution mainly in econometrics for binary time series count autoregression. So count autoregression will be adapted to the previous case if you want to predict the number of cases of a dengue. Garch processes, and also some recent work about beta autoregression, which model, in fact, the dynamic of some time series with values between 0 and 1 with the beta distribution. So I think that it is an econometrics motivation, but I think that it could be important to model the dynamic of the proportion of spaces across the time. And this could be also have an interest in ecology. So the main point is that there is no general framework, no general approach available for studying some time series model when you try to incorporate some exogenous covariates. So the next question is what do we call exogenous covariates here? So you have many notions of exogeneity in the econometric literature. So it's not so easy to have a complete overview of all of them, all of them, and in particular the various links that you have between all of them. So I will mainly focus on something which is called strict exogeneity, and which was discussed by the previous call by Eric Renaud. So I suppose that YT, the outcome at time t, will be independent of the future of the covariate, the present value, conditional on the past value of both series. So this type of exogeneity will be quite relevant if we go back to the initial example that I presented. For instance, if you look at the temperature, so the past value of the temperature of the dengue cases will probably have an influence on the present values of the dengue cases, but in turn, what will happen on the number of cases for the dengue will probably will have no longer any influence on the future of the covariates. So for some time series X, it is quite relevant in connection with the example that I will present. So another property, which is called Granger non-causality, which can be related to the strict exogeneity notion, but only under an additional regularity condition. So Eric explained this very well in the last talk. And this means that when you try to predict X at time t using present and past value of the outcome and past value of the covariate, you don't need to put the present and the past value of the outcome. It's not necessary. So this gives another point of view related to this notion of strict exogeneity, even if in general it is not completely equivalent. So there are some other notions of exogeneity that are more complex, but that I will not discuss here because that one will be interesting for two reasons. First, it is compatible with some problems that I discussed at the beginning of the talk, and I will make a connection between this notion of strict exogeneity and another notion which comes from probability and which is called process in random environment. So what are the models that I will consider? So I will consider some models that are called observation driven. And the principle of this model is to define a bivariate Markov chain. So conditionally to past value, Y is defined by a conditional distribution, a one parameter distribution. So here I only focus on a univariate response, but it can be possibly extended. And this distribution is called P. And you replace the parameter of the distribution by a latent process, and you put an autoregressive structure on this latent process. So here you have some exogenous information that will enter in the dynamic. So this type of model are widely used. You have many examples of this type of process in the literature. For instance, you can model count time series using a Poisson distribution for P. When you take the Bernoulli distribution, you can recover the logistic autoregressive model or the probit autoregressive model. So it's a binary time series. And for instance, when you take this kind of distribution P, so you recover a well-known model which is called Garch in econometrics and finance. Right. So for this class of models, since I specify the dynamic conditional on the whole path of the process, and I specify it by assuming that the future value of the covariate will not depend on the state of the process. So there is a link between what is called strict exogeneity and what is called in probability random environment, since I specify the model directly conditional on the whole path. So conditional on X with this type of specification, we can check that the process, the latent process lambda t, is a non-homogeneous Markov chain with transition kernel that are random and that depend on the covariate. We can also see that the bivariate process, because the quantity of interest is Y, is also a Markov chain in random environment, but the main point will be first to study this non-homogeneous Markov chain that will define the lambda process. Okay, so in the literature of Markov chain in random environments, you have many seminal contributions, but the assumption or the setup is not convenient for the problems that I will investigate, because the state space is often either discrete or it satisfies, the kernel satisfies some doubling type condition or uniform contraction condition. So this is not the cases that I want to investigate. And for instance, if you look at the lambda process is a quite complex thing, especially if the variable y is discrete, because when you iterate this autoregressive function, you obtain an infinite function of the path value of y. And typically, this function, the distribution of lambda will be continuous, but not necessarily absolutely continuous. And in particular, you cannot apply the classical theory of irreducible Markov chain. So this adds another difficulty when you have a discrete state space for the y, but the lambda is continuous. Okay, so the next point is how can we define a stationary solution to this recursive equation? The main approach is to try to define the marginal distribution of lambda conditional on the covariate process. And this distribution that I denote pi t, of course, you have a time inhomogeneous Markov chain conditional on this environment. It will be solution of this invariance equation. So the main point is that when you look at this equilibrium equation, and when you iterate this equilibrium equation, you can write this pi t as pi t minus n at time t minus n times the various kernel between time t minus n and time t minus 1. So the main point is a natural way to define some candidates for pi t is to look at the almost sure limits of the backward iteration of the chain, which are given by there, where you initialize by measure mu, and you try to show that there is a solution. And in favorable cases, we will have a single solution. And we can also get some ergodicity results. So this is the general principle. Okay, so I will present now two results. So the first result of stationarity is obtained using a contractivity assumption. And I will present in the second step a second result, which is more involved. And this second result uses only a semi-contractivity assumption. So a good way to study this kind of dynamical system, random dynamical system, is to get an almost sure representation. So here the model is defined by a conditional distribution, but I suppose that everybody knows that it is possible to represent almost surely a distribution using the inverse of the CDF associated to the distribution P and using some uniformly distributed random variable over 0, 1. Okay, so now I suppose that I represent the process like this with a sequence of uniform that is independent from the exogenous variable. And using some assumptions, so you have some assumption of integrability, and you have this important assumption, which is A3. We have a random map that defines the dynamic of the lambda process, which is given here. And I suppose that I have a contraction with respect to the value of the latent point, a Lipschitz condition, with a Lipschitz constant, which is called kappa, but kappa is a function of the environment. And what I put as a condition, I put a quite weak condition, which is usually called the Lyapunov condition, so saying that the expectation of the logarithm is negative. And if kappa is deterministic, it means that kappa is between 0 and 1, strictly. But when you have a random quantity, a random function, it does not mean that you have a kappa between 0 and 1. With positive probability, kappa can exceed 1, which is quite interesting in terms of generality. Okay, so to check A3 will be satisfied every time you take a distribution P, which is Lipschitz in terms of what we call a Wasserstein distance of order 1. So this is the condition that is written here. And then you simply impose a contractivity assumption with respect to the first and the second coordinate of the function. So I think it's not G here, it's F. So it's a mistake. Still with this Lyapunov condition, but now on the sum of between alpha and beta. So if you have this and under an additional log moment condition, which is not very restrictive, there exists a stationary and ergodic solution for this recursion, and the distribution of such process is unique. And if you look at in terms of moments, we have a conditional moment that is finite. So it's more difficult to get the unconditional moment. So for the moment, I have no general result. It's a bit tough if we work with such a general assumption, but at least we are sure that there exists a stationary and ergodic solution. So it gives a sense to some statistical problem, such as the inference by a maximum likelihood or pseudo maximum likelihood estimator, which usually only need the existence of a stationary and ergodic path. So first example, I will only give one example, but there are many others. So when you take a Poisson autoregressive process with a random intensity lambda t, that is autoregressive, so you can consider, for instance, this linear specification for the intensity with random coefficients. And these random coefficients can model, for instance, some interaction properties between the covariates and the lag values of the response. Or it can also be used to model with threshold, which means that depending on the level of the environment, it will affect the dynamic and the parameter of the model will change in function of the value of the exogenous process. Okay, so this is the first result that we can obtain and which give already some possibility to define some model. So now I will use, I will present another result, which is based on semi-contractivity. So here I will try to investigate more general structure for this observation-driven model in random environments. So to define some complex model, I want now to consider some models for which we can put some threshold. So we can put some threshold for the covariates, but we can also put some threshold for the path values of the outcome. So meaning that we want to get a general thresholding autoregressive model. And this case is much more difficult because if you look at the structure of the function f, it is continuous with respect to s, but it is not necessarily continuous with respect to y. So in this sense, the previous fully contractivity approach that I presented before is no more valid. And this creates an additional technical difficulty. For deterministic environments, you already have some studies about the existence of threshold model for Poisson autoregressions, but nothing exists, for instance, for the case of exogenous covariates, that is with a random environment. Right, so I will make some assumptions. So the first assumption in this new setup, I will consider that you have only a contractivity assumption with respect to the first argument, that is the value of the latent process. So I assume a contractivity with respect to S, always with this kind of general assumption of Lyapunov exponent. And now I will assume a second assumption, and this assumption will give birth to, say, a Lyapunov condition or a drift condition. But we can write more general condition, but here it's more a practical condition in the sense that I assume that the function f is sublinear. So sublinear possibly in a power of I, but in the integral of this power of I will be sublinear with respect to S. So this will give automatically a Lyapunov condition for a power for a power function. And in the assumption B3, I will assume that when you change the parameter, you cannot have completely different distribution. That is the distribution P when the parameter is S and when the parameter is S prime. So typically, it's not possible to take some orthogonal distribution. You cannot have some disjoint supports, for instance, for every S and S prime, but they can be, one could say, asymptotically singular when the distance between S and S prime goes to infinity. And the rate at which this distribution can be asymptotically singular will be given by the inverse of an exponential function. So, okay, with this polynomial here, so it's, yeah, it gives a wide range of possibility, even if it's not so easy to in a practical way, to always check this condition. So now I will present the result. And okay, so if these three assumptions are true, there exists a stationary and ergodic solution, and the distribution of such process is unique. So here the technique is much more complicated. So with respect to the contractivity results, for the contractivity results, the goal was to prove a convergence of the backward iteration of the chain in Wasserstein metric. So here it's also the case. It is in Wasserstein metric, but we don't use autoregressive representation as in the previous case, and we use a coupling method. And we adapted carefully the maximal coupling method to take in account of the environments and to make the things to make the backward iteration converging in a Wasserstein type metric. But the arguments are more difficult. So now, if you can still consider with this case Poisson autoregression, but with a more general structural assumption on the function f that will work with the previous power 1, for instance. So now another example that is interesting concerns the case of binary time series. So for instance, you can still consider the geologistic model of the probit model. And if you consider this recursion for the lambda process, so with a linear specification with some random parameter, so typically, up to some logarithmic integrability condition, we only need this to consider this contraction condition with respect to the first coefficient, and there is no constraint on the coefficient with respect to the y, and this is mainly due to the fact that the state space is bounded. It is 0, 1. But what I showed here for binary time series can be general to other type of categorical time series, that is with more than 2 outcomes. And this is the general things that I want to mention. So I present two types of time series, Poisson autoregression or binary autoregression. But there exists some extension, and you can recover some results. You can define some model with a very irregular structure on the latent variable. For instance, for Garch processes, we can take other type of count distribution. For instance, the negative binomial, which is always interesting to model the over dispersion of the data, which is not possible, of course, with the Poisson distribution. But for the last set of assumptions, what is quite difficult to check in practice is B3. But at least we can still define some interesting classes of models. So what was interesting with this approach is that when we formulate the things using the Markov chain in random environment setup, it is interesting this approach is quite interesting to extend this classical theory by investigating the limiting property of this backward iteration. So I only presented some results about autoregressive processes of order 1. So it could be possible to put higher order autoregressive processes. Maybe it will have some technical difficulties, but actually I do not think that the technicalities will change very much. Other possibility, and which will be probably more compatible with the data set that I presented at the beginning of the talk, could be to extend this to seasonal models, that is to take in account of seasonality and the same of exogenous covariate. So this also could be possible. And the other important thing is to take in account of possible non-stationarities in a sense too precise. Maybe we can imagine that you have some trends, especially in the climate variable. But what is difficult with non-stationarities, it is always necessary to precise which type of non-stationarity you want to take in account. It's not the same if you take, for instance, a deterministic trend, or if you take a random trend with a unit root problem. It's not exactly the same set. Okay, so this extension could be interesting, but I think that this work can represent the basis for at least a starting point for studying this model with exogenous covariate. And I have a series of papers now in which we try with several co-authors, and in particular Kostas Fokianos, Max Insoudabali with my former students, and Paul and Michael Neumann, which we will give a talk just after. And we investigated several setups in which you can get this mathematical framework to use the covariate in some standard time series model. And I think it's a bit early, but I have now finished, so you can ask questions because I suppose we have time. So thank you.
Thank you very much. So thank you for this nice talk, really, a very impressive one too. And maybe there are alternative questions concerning your talk, or who would like to ask anything? I think we discussed a lot concerning those works, so I would be happy. So please go ahead.
Again, sorry. Yes, thank you, Lionel, for this talk. Very, very thought opening, I would say. It turns out that in recent development in financial econometrics, people have put some new observation-driven models where this guy Simiet Koopman in Amsterdam, I don't know if you are following his work,
yeah.
but basically they put some dynamics through the score.
On the score, yeah, I know.
Yes.
This. Yeah.
Okay, I was thinking that this guy may provide to you a battery of specific models, for which you could check your contraction properties and so on.
Yeah. Probably. I don't know. So typically they use some this kind of model without covariates, I think.
Yes.
So I think the theory is defined without this exogenous covariate.
Yes.
But this could be a last step because, of course, I present this observation-driven model. So this is a class of model that is widely used, but of course, this is not the only class of model. And you have many other many other classes of models that are interesting, and it should be interesting to investigate it, I suppose. So maybe it could be a good idea, and when we have time.
Okay.
Thank you. I don't know if there are any more questions. I suggest that we have a 3-minute break before the talk of Michael, and we come back. So we follow strictly the schedule. I think it's preferable because people who want to attend one talk and not the other maybe would be happy of that. Thank you very much, and see you within 3 minutes.
Paul, j'arrive plus à lever le partage d'écran. Ah, c'est bon, tu m'as, voilà. C'est trop bien.
Thank you. Hello, Michael. Do you mind to wait just like 2 minutes and we begin on time?
No problem at all, Paul.
Thank you.
Can you also already try to share my screen?
Yes, please.
I press share screen. Okay. So wait, please. Okay. Paul?
Yes.
Can you see my first slide?
No.
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 Um,
I think we didn't share the right one.
what should I do? I have a button share screen. I press it again. Okay.
You press it and you choose the right file.
So, and can you see my first slide now?
No, at the moment, no.
Oh, shit. What can we do? I'm again in the menu of the Zoom session.
Yes, so downstairs you have share screen.
Okay, I press it once.
You must select the convenient file.
What do you mean by select? I press this button, share screen.
Yes, you
okay.
share the screen and you will have the list of opened documents.
No, I don't see any list.
Wow.
My browser does not allow to share the screen. Oh, okay. Video.
Shall we do so? Maybe I could do it for you if you prefer, because I think
disabled. Paul, it's your fault. The host disabled to share my screen.
Really? Wait. Really? Because I can also try to open it and to make it possible if you want. If you want, because apparently nobody can see it, and in fact, Maxence gave you the rights, so I don't know what happens. Wait, I can do it. Maybe I can do it for you. Can you? Else I can share your screen. No, but this is me who did that.
Okay.
Yes, so that means that in fact this is.
Yes, but wait please, Paul.
Yes.
Can you see my first slide now or not?
Wait.
I switch from the first to the second slide. No?
I don't see anything. I'm sorry.
The point is, when I try to share screen, I press this button in the bottom line of this Zoom. I don't get a list of possible things.
If you prefer, I can do it for you, and you tell me to pass the slides, and I will do it. Do you want that? Maybe we should try it, because I fear else we will lose time, and that's
I see.
That's yours. Is that okay?
This is my first slide.
Yes, I know this. So please, let's go ahead, and you just tell me to go to the next one. Okay?
Okay, Paul. Okay, we could do it this way.
Yes. So thank you, Michael, for accepting this invitation. That's a pleasure. And so please go ahead. Sorry for these technical difficulties.
Okay. Thank you very much, Paul, for inviting me and for setting up this interesting conference. To the others, we had some technical problems with my slides, and therefore I will try to cooperate with Paul to show you all my slides. So, Paul, next slide, please. Okay, here, this is a plan of my talk. Actually, it will consist of 4 parts. In the first part, I will do my best to provide some motivation for this work. Then I briefly review the classical non-parametric isotonic least squares estimator. After that, I present a modification of it, and this modified estimator is exactly that what we want. We are then able to prove the desired and hopefully optimal rate of convergence for this. And finally, I will conclude. Paul, next slide, please. Okay. So the starting point of our investigation was the following one. We were working already for some time on integer valued time series models, and we were thinking about possibilities to estimate these models. So quite common assumption is for such integer valued time series that the observations yt given the past have a Poisson distribution, and the intensity lambda t is also random. Paul, next part of the slide. Yes, and this intensity lambda t may depend on lagged values of the y process, on lagged intensities. Maybe there's also some trend, and also exogenous variables are possible, these CT. Paul, next part of the slide. Okay, this is what I have already said. Next part. Okay, we can rewrite this model in the form of a non-parametric time series regression model. And what is important here is the conditional expectation of this error given the complete path is 0 almost surely. So next slide, please. So now for such a non-parametric regression model, we were seeking a reasonable non-parametric estimator, but we experienced a particular challenge here, namely the explanatory variables are most probably not regularly distributed. So that means, in other words, common non-parametric methods, kernel estimators or whatsoever, are perhaps not suitable. And moreover, such methods like kernel estimators require the choice of a method parameter, a bandwidth, and in particular in this time series context, the choice of such a bandwidth is not an easy task. So next slide, please. On the other hand, when we consider, for example, one of the simplest models, namely such a linear integer valued autoregressive model of order P, then next part of the slide, then a natural condition on these parameters is that they are all non-negative. And in this case, it turns out that the corresponding function f, next part, is isotonic. Isotonic means non-decreasing in each component. So next part or next slide. So let's assume that we have such a non-parametric time series regression model. IT denotes the information variable. And as before, we assume that the conditional expectation of epsilon t given this information variable is 0, and the function f is isotonic. So the classical approach to estimate this function f is given by the so-called isotonic least squares estimator. This is just an usual least squares estimator with the additional side condition that all candidate functions g have to be isotonic. So next slide. So one obvious advantage of this estimator is that there's no bandwidth choice necessary. This is obvious, and in particular, in the context of time series data, the appropriate choice of a bandwidth is quite often quite cumbersome, and therefore I think this is a real advantage. So in dimension 1, it is also well known that even an irregular distribution of the explanatory variables, of the information variables, doesn't harm. and we get the rate of convergence as the sample size tends to infinity of n to the power minus 1/3, which is actually the optimal one in this case. So next part of the slide. So moreover, this assumption of isotonicity seems to be appropriate in many cases or in many applications. For example, many parametric models for integer value time series produce automatically such an isotonic conditional mean function. In this sense, our contribution is just an extension of previous work. Applications in many areas are possible. I don't want to pretend to be a specialist in applications, but you will find in the literature, I mentioned only this one paper, really many applications in different fields. So next slide, please. So one interesting thing is, and this is already known for a long time, that the classical isotonic least squares estimator has such a max-min or min-max representation. Next part of the slide. Paul, yes. And here we have to take localized averages of the observations. And next part, the set L is a so-called lower set, and the set U is a so-called upper set. Next part. And here's a picture which shows what is meant by lower set and upper set. The blue one is just an example of such a lower set. The yellow one, an example of an upper set. Here, maybe you see this tiny point x. If this is a point x where you want to estimate the function f, then this is actually done by averages over these intersections of lower and upper sets. And this is shown by this green field. So next slide. So before I turn to a modified estimator, let me say again that in dimension 1, there's no problem at all with this classical isotonic least squares estimator. It can be easily analyzed, and the rate of convergence is actually the optimal one. So next part. So in higher dimensions, it is also known for a long time that this classical isotonic least squares estimator is consistent at the points where f is continuous. But actually, we were not able to prove that in higher dimensions that this estimator attains optimal rates of convergence. The problem is there exists actually a huge number of lower and upper sets, or in other words, entropies are very large, and this is basically the reason why we were only able to prove suboptimal rates of convergence in this context. So next part. Okay, for example, this is one reference where this problem also appears in density estimation. Gauer and Wellner also obtained only a suboptimal rate in dimension greater than or equal to 2. And again, the reason for this is just the huge number of possible candidate lower and upper sets. So what is the modification of this classical estimator? We, instead of arbitrary lower and upper sets, we consider only lower and upper rectangular type. So next part of this slide, Paul, here. Here here in blue color, you see a possible lower set, and in yellow color, a possible upper set, and both sets are of rectangular type. And when we consider intersections of these sets, this means we have to take averages over such hyperrectangles in higher dimensions. Okay, so next part, please. Next part. Okay, it turns out that these modified estimators are also isotonic just by construction. And we were actually able to show that these estimators converge with the optimal rate of convergence. And as before, also as for the classical isotonic least squares estimator, a bandwidth choice here is not necessary at all because of this min-max or max-min construction. An appropriate degree of smoothing is automatically found. So one possible estimator is just the mean of these two estimators, Fn1 bar and Fn2 bar, which are actually good enough. So next slide, please. So now I would like to come to the main result. So for simplicity, consider this special case where the domain is just the d-dimensional unit cube. We assume that the function f is isotonic and in addition bounded, and for simplicity differentiable. That means, in other words, because of boundedness and differentiability, that the L1 norm of the first partial derivatives is finite, or in other words, the degree of smoothness is equal to 1. So it's well known that for degree of smoothness 1 and for dimension d, that the optimal rate of convergence is n to the power minus 1 divided by 2 plus d. So next part, please. Of course, we have a smoothness assumption only in an L1 sense. We don't have a smoothness point-wise smoothness assumptions. Therefore, there's no guarantee for good point-wise behavior of any estimator here. But we can hope for a good estimator of the good behavior of the estimator in an appropriate L1 sense. So here we match the norms which are responsible for the smoothness and which form the loss function. In both cases, we consider the L1 loss. So next slide, please, Paul. As before, we assume that we have such a non-parametric time series regression model. Dimension is d. The function f to be estimated is assumed to be isotonic and bounded. Next part. The information variables form a stationary process, and again, for simplicity, we assume here that the IT have a continuous distribution. Then these conditions on the errors epsilon t. So next part. And we assume that somehow the, say, density of the information variable is bounded away from 0 and bounded away from infinity. This is more or less described by this more complicated formula. So next slide, please, Paul. Okay. In addition, we assume that the process formed by the information variables is strong mixing. So a special case is that the information variable has actually a density which is bounded away from 0. So for some technical reason, if we would use, for example, a non-parametric kernel estimator, then Hn would be the optimal bandwidth. This HN would be that bandwidth which provides an estimator with the optimal rate of convergence. So it is well known that all these non-parametric isotonic estimators have problems at the boundary of the domain, and therefore we just drop the boundary from our considerations. We consider the behavior of this estimator only on the interior of the domain. This is denoted by dn. So next part of the slide. Okay, and this is just our result on the asymptotic performance of this estimator. The L1 loss of this estimator decays at the rate n to the power -1 over 2 plus d, which is actually the optimal rate of convergence in this context. So next slide, please. So here's a very short sketch of the proof. So first of all, we have to get rid of these absolute value signs. That means we consider the non-negative and the non-positive part of the loss separately. So next part. So let's focus on this non-negative part. Then, because of this min-max construction, we get an upper estimate by just replacing the minimum by some fixed point Bn. So next part of the slide. And what we do next is to split up into a Bayes term and a variance type term, and both terms can be treated separately now. So next slide, please. Regarding the Bayes term, it just follows from isotonicity and from boundedness of the function f that the integral over the Bayes terms is of the desired order. And regarding the variance term or stochastic term, we just use a classical fluctuation result by Bickel and Pichura, and we also obtain the desired order of convergence, this time convergence in probability, of course. So next slide, please. So here's a brief summary of my talk. We considered the non-parametric time series regression with the isotonic function f. Actually, the general case, which we also considered, means that the information variable may consist of lagged values of the process y. It could also contain exogenous variables or a trend. All these things are possible. So next part of the slide. So as said before, or as already said, this information variable can consist of several components. F was assumed to be isotonic and bounded, and maybe last part of this slide. So as said before, one really nice and convenient thing is that no choice of any sort of smoothing parameter is required here. This estimator automatically adapts to the necessary and adequate degree of smoothing, and the rate of convergence that we obtain for this estimator measured in the L1 norm is just the optimal one. So I guess that's all. Thank you very much to Paul for helping me with my talk because of my technical problems. And if there are any questions, don't hesitate to ask these questions. So.
Thank you very much. This is not a problem. And so, yes, if there are, so I stop the sharing because it will allow people to make easier things. And so thank you very much. So do you have, does anyone have any questions concerning this nice talk? Okay. So what should I say? And so in this case, I suggest that we keep on for in contact for other questions. And oh yes, so let's go back at 3 p.m. Paris time with Thierry's talk. And thank you very much for attending the talk. And thank you very much for giving it. Thank you. Let's stop. We can. I think we should just stop the. Sorry. What? Yes. Okay. Let's stop. Thank you very much. On peut faire une pause.